Hello and welcome to another WJEC A level physics question. This is question 4 from June 2015's Unit 5. It's a radioactivity question which nowadays is found in Unit 3. So what we've got is technetium-99 is only emitting gamma radiation. An experiment was carried out to show this, and various absorbers were placed between the source and the detector at the time shown in the table below, and the mean count rate was obtained. The results were plotted on a graph, and the decay curve for the technetium-99 itself has been plotted, so that's the dotted line on the graph there. First thing we're asked to do here is to determine the half-life of the technetium-99m. So the half-life would be the time in which the count rate would drop to half of its initial value. The initial value is 450 counts per second, so we're looking for 225 counts per second. If we draw a line across here, we will find that that's at about 360 seconds. Every 2 squares is worth 10 seconds there. Sorry, minutes, not seconds. So simply going to say 360 minutes, and you get a little bit of leeway there in the exam, depending on how carefully you've read the graph. Next, we've got to explain why the results are consistent with the technetium-99 only emitting gamma radiation. Well, the first thing is, with paper in the way, there's no noticeable drop in the count rate, so therefore there's no alpha. So let's put that down. So no drop with paper, therefore no alpha present. Next, if we look at the graph, there is a drop with aluminium, so you might be excused for thinking that that meant that there was a small amount of beta radiation in the source, but we've been told that there's only gamma radiation, so we've got to explain why there's this little bit of a drop with the aluminium. That will simply be that the aluminium is absorbing a small amount of the gamma. So let's put that down. So drop with aluminium is due to a small amount of gamma being absorbed. And then finally we note that even with lead there, the count rate basically drops, sorry, not even with lead, but with lead the count rate basically drops down to 0. But we also can realise that there must be gamma there, because only gamma can penetrate the aluminium. For the next part of the question, the detector only detects 0.6% of the gamma radiation emitted by the source. That will be because the radiation from the source is probably travelling off in many directions, and only part of it is actually entering the detector, probably a Geiger-Müller tube. We're going to use the graph and the half-life of technetium-99 to calculate the initial mass of technetium-99, and given that the mass of a technetium-99 atom is 99 U's. So let's do this in bits. The initial activity from the graph, or the initial count rate from the graph, is 450 count rates per second. So what we basically got is that 450 counts per second is 0.6% of the initial activity. So if we rearrange this, the initial activity is 450 times 100 over the 0.6, which will give us 75,000 becquerels. We can use a decay equation if we wanted to. Sorry, we don't need a decay equation for this one actually. What we can use the half-life to work out is we can use it to work out the decay constant here. So the decay constant, lambda, is log 2 over the half-life, but we're going to need to turn that half-life into seconds. So we went for 360 minutes. Let's just double check that. Yeah, 360 minutes. But we've got to turn those minutes into seconds. So that gives us a decay constant of about 3.2 times 10 to the minus 5 per second. Now we can work out the initial number of nuclei, because we can use A equals lambda n, or more specifically A naught, the initial activity, is lambda times n naught, the initial number of nuclei. So the initial number of nuclei will be A naught over lambda, and we've worked out A naught as 75,000 becquerel, and lambda is 3.2 times 10 to the minus 5 per second. So that gives us an initial number of nuclei of about 2.3 times 10 to the 9. Now each one of those nuclei has got a mass of 99 U's, so the initial mass here, m naught, is going to be the number of nuclei, 2.3 times 10 to the 9, multiplied by 99 U's, where a U is 1.66 times 10 to the minus 27 kilograms. Giving us a final answer of 3.84 times 10 to the minus 16. And we mustn't forget the unit of kilograms, and in fact it was a unit mark for this particular paper. Thank you for listening. Please remember to like and subscribe, and feel free to add comments to this video. Goodbye.